Carqueville visiting us from Stony Brook this week, and he will be leaving tomorrow, so today is your last day to catch him. And he will tell us about his work on topological defects and generalized orbifolds.
Thank you.
Take it away.
Thank you very much for the invitation. I'm glad to be here. I shall talk about topological defects in two-dimensional quantum field theories and how they give rise to various sorts of dualities. In particular, I want to try and explain how defects can be used to understand and describe everything we know about orbifolds by symmetry groups, and then also how defects can be used to widen the scope of what we can mean by orbifold, so that we have orbifold theories without mentioning any symmetry, with any symmetry group there at all. The plan to do this is roughly in 3 steps. First, I want to take some time and introduce the natural language, how one can talk about defects in topological field theories, which is mostly diagrammatical. Then I'll introduce one particular class of models, two-dimensional Lambda-Ginsburg models, and explain how the structure that we'll argue for heuristically manifested itself very concretely for Lambda-Ginsburg models. And then later, with all this preparation, it will be easy to present and understand several, I hope, interesting applications of this whole theory. So let's start with the typical situation in topological field theory with defects. So everything starts from the world sheet, and here I show a particular part of the two-dimensional surface. Some could be any Riemann surface with many boundaries and many handles, but here we only look at this. There can, of course, be insertions of fields, like here, phi 3, phi 4. But as you see, there's also one-dimensional things embedded into the surface, which are particular lines. Is that chalk here? And I want to consider decorated surfaces that do not only have points that are labeled by field insertions, but also one-dimensional lines, which I want you to think of as generalizations of boundary conditions. So if the blackboard is my surface, and let's say it stops here, then there can be a boundary condition which is always oriented to me, often called X. And there's some theory to the left side, and then there will be conditions on the fields that come from the bulk of the theory of the surface and approach the boundary, and therefore we talk about boundary conditions. But of course, we can also have lines where there's conditions on the fields both to the left and to the right. So ordinary boundary conditions, which in string theory are interpreted as D-branes, are the special cases of defect lines or interfaces, where on the one side of the line is the trivial theory, namely node theory. But here, as you can see, you can have many different theories. They are called T1, T2, T3, and so on here. And there will be special conditions on all the fields. But we don't allow all defects. So if it's a topological field theory with defects, then what a topological field theory with any field theory wants to do is to compute correlators. And by definition, a topological field theory with defects does not depend on the precise location of all the insertion points of the fields and the precise location of the defect lines, but only on their location up to isotopy. So if I change the location a little bit like here, the value of the correlator will be exactly the same. Maybe I should have said the kind of theories that are considered here, like T1, T2, are any two-dimensional quantum field theories, though for me they will be conformal or probably only topological. It's the same topological field theories, but they can come from the twist, the A or the B twist of the sigma model, the Lambda-Ginsburg model, certain WZW models are possible, and in many other theories. Okay, if we're in this situation, there's a few immediate algebraic things that you can extract out of this, namely certain products. So I said that so often my arm will be a defect line, there will be a theory here and a theory there, but there can also be another defect with a third theory over here. Since the precise location of this defect line doesn't matter, as soon as I don't get across the field insertion, I can look at the limit where the two defects approach each other. And since it's a topological field theory, this limit is well defined and non-singular. Just like the just like something else that I want to discuss in a minute. So you see, you have a sort of product of defect conditions where you just fuse them together. This is a product because, I mean, by this image, you immediately believe me that it should be associative, so I can first fuse them together and then fuse a third defect, or first fuse these two defects and then fuse my arm to the product. This product also has a unit. It's the defect condition which doesn't come with any condition. It's the invisible defect or the identity defect. So all fields can just go through and it doesn't change the correlate then. Sometimes I don't show the invisible defect, which is always called I. Don't show it at all, or it's displayed by a dashed line. Of course, it's also a right unit. So there could also be an invisible defect over here. The fusion of two defects, X and Y, will be denoted by a tensor product for a reason that will become more obvious in a second. So this is one layer of a product structure, an algebra structure. But there's another layer, which is actually familiar, I think. So if we now fix two theories, theory A and theory B, say, then we can still look at all the possible defect conditions or interfaces between these two given theories. So fix a pair, and then there might be many different defects, maybe X, X prime, and X double prime. Maybe I want to put this here. So here's a theory that I want to call A, theory B, and then here is a field phi, here field psi, and this is the defect X prime, and here's the defect X double prime. Just like boundary conditions, where these would be boundary condition changing operators, interpreted as over strings in string theory. These are now defect conditions and their fields. And just like bulk fields and boundary fields, they can approach each other. And since we're in a topological theory, this product is again well defined. If the topological field theory comes from the twist of an n equals 2 superconformal field theory in 2 dimensions, then you know that this twist, the associated topological field theory, precisely captures the structure of the chiral ring of the supersymmetric field theory. And the chiral ring has an associative product which is associative on the nose. So this is what we have here. And this multiplication of local fields, or fields that we insert at points, is always denoted vertically, and we write the fusion of defects horizontally. Of course, the operator product of fields also has a unit, both from the left and from the right. We want to read these diagrams always from bottom to top and from right to left. And this is simply the identity, which is the vertex operator associated to the vacuum. So let me stress again, there's two layers of structure. We have multiplication or fusion of defects and multiplication or operator product of operators. So everything that I've said so far, and that these two things are associative, is nearly all the content of the following statement, which rigorously was first established by Davidoff, Kong, and Wonken, which says that the structure that you find for any topological field theory with defects is that of a bicategory. That is a structure of categories within categories. On the next slide, I want to recall the definition of this thing, but it is among others, it is these pictures which are very natural from the point of view of pictures or physics of two-dimensional field theories, which is encapsulated by this mathematical notion of a bicategory or weak to two category. And any such gadget comes with three layers of structures, namely the theories, which we associate to the domains on the worldsheet, to two-dimensional parts of the worldsheet. Then they are called objects. Then there's the defect lines, which are will be referred to as one-morphisms. They are associated to one-dimensional things, namely to lines. And finally, the fields, they are inserted at points, at zero-dimensional things, and they are called two-morphisms. So I want you to think of a defect as a map between the theory to the right to the theory on the left. So this is a morphism or a map, and then a field inserted on the defect or on the junction of two defects will be a map from the lower defect to the upper defect. Okay.
So, probably should have asked you this before, But if I consider this situation on a higher genus Riemann surface, then for standard topological field theory with just local insertions, right, I know that I can reduce it to spheres with 3 punctures and glue and so on. And these are like standard axioms of PFT. So in what happens to that structure with defects?
I wish I knew.
Okay.
So that's a very good question. So if you only consider the closed sector, no boundaries, then it's simply a certain kind of algebra. Fourier's algebra over complex numbers, which is commutative. If you have no defects, but those which are boundaries, then a topological field theory, an open-closed topological field theory, is such an algebra together with a category which describes the boundary conditions of rings and open strings, which needs to have a property that is called Calabi-Yau. There must be maps between the category for every object and the bulk field, which are the bulk boundary and the boundary bulk maps. And an open-closed duality condition, the Cardi condition, must be satisfied. So this is just recalling that we have a good algebraic structure which computes everything from genus 0 also the open-closed case. In the case of defects, arbitrary defects, it is not known what the best way to do this in terms of this generator and relations approach. So there's an infinite number of generators, but what the minimal amount of relations is not known. And very smart people have tried and have not succeeded so far. But there's more to say. There's some natural guesses, and actually much of my talk can be interpreted as, well, we don't know this, but definitely this structure must be there. So let's ask what comes out of this structure.
So it's something with defects which are boundaries. Is that the case with boundary conditions, or sort of intrinsically just factorized more?
If one of the two theories to the side of a defect is trivial, then I call the defect a boundary condition.
I see.
If both are non-trivial, then it's a proper defect or interface.
Can I have it where they're both non-trivial, if the boundary condition doesn't talk between the two?
Oh yes, that would be that's another good question.
Like,
This is so then nothing could go through, right? This would be what's the one? If you have a defect and then you fold, then you have this kind of thing, right? You have two theories with two boundaries and then you tensor them together and then unfold. That's what you're talking about. That's one particular kind of defect, but there's many more.
So how does one theory know about the other? If they communicate, or
It depends.
Or why don't you have just two separate things?
Right. If we're in the situation described by Daniel, then they will not communicate. Then it will completely factorize in some sense. But if some information can go through, in a sense to be discussed in more detail, then it will not factorize. So then it's more complicated. Then you have to glue together in a certain way, and gluing together can be complicated.
One more question. Maybe you said this. Do you assume some sort of locality on the boundary condition? I mean, I can imagine something where a field coming in here is the same as a field up here.
Oh yes. This comes out of the axioms. Yes, this is part of the conditions that the boundary bulk maps and similar maps have to satisfy.
There will be a locality.
Yes, that's great. Okay, so definition and theorem, repackaging what we said earlier, and unpacking a little bit of this as well. So if you have any TFT with defects, then you can associate a bicategory to this. As I said, a bicategory is made up of objects, and they call these objects A, B, C, and so on. And then there's, for every pair of objects, A and B, there's another category of defect conditions. So remember that a category, again, is made of two things, of objects and maps between the objects. So if we fix two theories or objects in the bicategory, then we will have a collection of all possible defect conditions between these two theories. These will be the objects of this category and the one morphisms of the bicategory. And in between these boundary conditions, there can be maps, which are fields that are inserted at the junction of two given boundary defect conditions, which here are called X and X prime, and X prime and X double prime. And the only thing, this word category, which maybe is not used every day, simply means that these maps between the objects in the category are associative and unital. That's all. So, and that's, as we just discussed, what you expect from the operator product expansion in topological field theories. So, between the object of the bicategory, which are the theories, we have the defect conditions, and between defect conditions, we can have defect condition changing fields, just like always. But then also we have maps between these collections of defect conditions, which go from A to B, and then from B to C. So if I have yet another one over here, and the theory C here, and then this is Y, then we can fuse them together. And these maps I don't call multiplication, but tensor product, or fusion. Therefore the tensor product symbol. And there's always the unit defect, which has no condition on all the fields, so it basically does nothing. So in particular, fusing with the unit leaves the thing invariant. So you have isomorphisms for any defect from A to B, so to the left is B and to the right is A, so you can fuse with the unit, in theory, B from the left, and with the unit or invisible defect or theory A on the right, and you get the same thing again. Because this fuses from the left, I call it lambda as left, and this isomorphism I call rho as in right. And it's associative. So one more time, the message that in this bicategory associated to any topological field theory, the objects are interpreted as the theories, like a WZW model or a twisted signal model. The one morphisms are the defects in between, and the two morphisms are the fields sitting on the defect line. The tensor product describes the fusion of defects, and the units are the invisible defects.
Do you always have a trivial theory?
There's always a trivial theory.
There's always a distinguished object?
Yes. Again, the picture. For a given pair of theories A and B, there can be a defect X in between. There can be another defect X prime. And then between these two defect conditions, there can be a field phi, which would be a two-morphism. Can of course also be a third field theory, C, and a defect Y between B and C. And this isomorphism here between I tensor Y and Y would be like this one here, only that now it's between different theories. I will later call this lambda because it fuses the identity from the left. There can also be very special defects, as we'll discuss at length later, between theory A and theory A, because there's no special, and they will be like algebras. I call them capital A. And since things could also curve, because everything is oriented, there can be a little island of theory B embedded in theory A by using this defect X, which goes from A to B. But now I have to tell you what I mean when I draw these pictures here, when there's a cup like so, or a cap like so. So what kind of map is this? That's the next thing I want to do. So Ilarion, part of my response to Ilarion's comment was that I want to say at least this structure must be there because the intuition in physics tells us so, and then we will draw conclusions from the presence of this structure. And the fact that things can take a U-turn will precisely give us the structure of a junction of defects. So what does that mean? Since these oriented defect lines can take a U-turn either in this direction or in this direction, we will always have maps. Again, I said that we read all these diagrams, which are often called string diagrams, though don't confuse the defect lines with strings and string theory. We always read them from bottom to top and from right to left. So this will be a map from something tensor X to the identity, because we don't see it. And this something should be the same defect condition as X, but only with the orientation reversed. So dagger means orientation reversal for defects. Similarly, here this is a map from the identity to X tensor, its orientation reversal. The reason why these maps are called evaluation and co-evaluation, it's a good one. I want to illustrate this. So let's consider a very simple example. It's not what I really want to talk about, but let's say that X is a complex vector space which is finite dimensional with a basis EI. Then the evaluation applied of x applied to EI star tensor EJ will be the evaluation of the functional EI star on the vector EJ, and of course this is delta IJ, and the co-evaluation, which is a number, and C is now the unit, right? Because if you have any C vector space and tensor over C with C, you get the same space again, up to a very trivial isomorphism. Now the co-evaluation will be a map from the complex numbers to the vector space X tensor X dagger. This is a very simple example. And in sense, I know what it does if I know what it does with the number 1, because if I multiply by some other number, then I get its value for any other number. And for my chosen basis, I can take this to be EI tensor EI star. We'll return to this example later. And now, of course, we know that for finite dimensional vector spaces, the dual of a vector space and the vector space themselves, they're naturally isomorphic. And one way to do this, to see this in this situation here, is by first recalling again that all the defects are topological. So in any correlator, in any worldsheet, I can draw a wiggly line like this straight. So we must have these identities, an identity like this one, and also an identity for the orientation reverse defect X dagger, like so. And now again, whenever you see such pictures, you read them from bottom to top and from right to left. And in particular, then this here is simply the identity, so it's not labeled at all, it's just a map from X to X, and the simplest map from X to X is the identity. But this is more interesting. So let's read it from bottom to top. Here, it seems like nothing is happening, but I haven't drawn the invisible defect. Really, there's a junction of X and the invisible defect, which feeds into the co-evaluation here. And the invisible defect is on the left, so I have the inverse of the left action. Some map from X to I tensor X. Then there's the co-evaluation. Then there's the evaluation with the invisible defect coming out, not invincible, invisible defect coming out, and then rho the right action on this. So I have a non-trivial identity between 4 structure maps, left and right action, evaluation, co-evaluation, and they should be the identity. So mathematically that's non-trivial, but physically it must be so. That's obvious because I can just draw it straight and then it should have the same value for any correlator. And you have a similar equation like this. Now, if the map's evaluation and co-evaluation between X and X dagger for all X satisfy this property, then one says that this bicategory has adjoints, because for every one morphism or defect X, there exists another one morphism or defect X dagger in the opposite direction. If X goes from A to B, and then the reverse one goes from B to A. And there are maps called evaluation and co-evaluation, going from having these domains and codomains as here in the first line. And we want that these identities here hold. Then X dagger is called the adjoint of X. And using these identities, you can prove rather easily that X dagger is actually isomorphic to X if X is a vector space that is finite dimensional. Some people, including me, like to call these groups here Zorro groups because it looks a bit like the Z of a Zorro. So that's for the first part, the last definition that I wanted to give.
So in this example where X is a vector space, thinking about it also as a morphism from one theory to another, what kind of theories would I have such that this is a defect?
That's a good question, but it will be much easier for me to answer it in about half an hour. It's not the kind of answer where I say, oh, I will definitely give you the answer and then won't, but I will. Okay. So we might share. Okay, any other questions regarding this slide? And the Zorro moves? No? Okay. So then, now that I've tried to argue that bicategories are very natural if you discuss defects in topological field theories, let me give you one of my favorite examples of field theories in 2 dimensions, namely Landau-Ginzburg models. The way that nearly everybody thinks about Landau-Ginzburg models is correct, namely that it's a 2, 2 supersymmetric field theory in 2 dimensions, which is a whole class of such theories, which are not conformal, but which we know to be very closely related to conformal field theories. We think that many CFTs can be regarded as the infrared fixed point of RG flow of the Ginsburg models or their own forms. Because of that, there's also a direct connection between Landau-Ginsburg models and 2D TFTs, and one has this under very good control. You'll see this a little bit later. Also, one can lift from mere topological field theory to topological string theory, either via some detour or straight algebraically, so this is under very good control as well. And it is matrix factorizations, which I'll review on the next slide, that describe both boundary conditions and more generally defects for Landau-Ginsburg models. And these are simple objects with which you can compute rather nicely, and which also manifest a lot of deep properties that you always have in topological string theory, topological field theory. Originally, these matrix factorizations were first studied in the early 80s, late 70s, in the context of singularity theory. And of course, there's also a strong connection between singularity theory and Landau-Ginsburg models for at least 25 years. Landau-Ginsburg models are one of the 2 or 3 pillars of neurosymmetry. Another one is Carqueville geometry, and then the extension of neurosymmetry from the bulk to also the boundary sector, so open and closed sector, and it's called homological neurosymmetry. There's something else called homological, namely homological link invariance. For physicists, often refined link invariance or not invariance, and Landau-Ginsburg models are one of the scenarios in which you can compute these interesting topological invariants, which also then have physical interpretations. And the way you do this is by understanding that the Ginsburg models give rise to certain types of tensor categories, namely the bicategories that we're talking about. Tensor because there's this fusion of defects. Okay, so how does this come about? I want to describe a Landau-Ginsburg, a bicategory script LG of Landau-Ginsburg models. So the first thing I have to do is to give you the theories, the defects, and the fields, so the objects, the one morphisms, and the two morphisms. The objects are precisely given by the F-term superpotential of the Landau-Ginsburg model. So the Landau-Ginsburg model has a D-term, which is not relevant in the topological sector, and an F-term, which is the superpotential of the 2D theory. And for the models I will study, they are simply polynomials, W that depend on some number of variables x, x1 to xn. And I want a certain condition, namely that the vector space, which is this quotient here called the Jacobian, is finite dimensional, because Waffer showed roughly 25 years ago that it is precisely this space, Cx divided by the ideal generated by all the partial derivatives, that describes the ring of chiral primaries of the CFT, which flows to which the Landau-Ginsburg model flows. So, but to cut it short, potentials are polynomials, and they are precisely the objects or the theories in the bicategory of Landau-Ginsburg. Now, what given two polynomials, W and V, where W depends on x variables and V depends on z variables, interpreted as chiral primary fields, what is a one morphism or a defect between the two? That will be a matrix factorization of the difference of these two things. So from W to V, it will be a matrix factorization of V minus W. And for the purposes of this talk, a matrix factorization simply is an odd matrix, capital X, which has entries that are polynomials in the x and the z variables, such that if you square the matrix X, then you get some other matrix, but not any other matrix, but one that is the identity matrix multiplied with only one polynomial, namely the thing that it factorizes, V minus W. So, an example, so a very important example, so I'll put it in the corner over here. If you have x to the I and x to the d minus I, that's an odd matrix. If you square this, you will find that this is equal to the 2 by 2 matrix, which is the identity matrix, times x to the d. That's a matrix factorization of potential x to the d. next to the D happens to be the potential that corresponds to the A-type minimal supersymmetrical form of field theory. But you see, it's something very simple. Matrix factorizations are just matrices with some polynomial entries that factorize a given polynomial. Something else that is simple is the space of two morphisms for two matrix factorizations x and y. So let's assume we have two matrices x and y, which might be of a very different size, and which both factorize v minus w. And what is the space of defect junction fields between x and y? And that will be, as is very typical in topological field theory, the cohomology of a certain BST operator. Now, as Kapustin and Lee and Desarroyo showed, the BST operator is the one that sends a matrix psi of a given size, of the correct size, such that the thing on the right-hand side here makes sense. A matrix psi that depends on the variables x and z, on which the potentials depend, to the following matrix. So y times psi minus a sign which depends on whether psi is an even or an odd matrix, times psi times x. Now you can do this again and send this via the same operator to y psi, y times this minus blah, this times x, and then use that x quest to v minus w and y quest to v minus w, and find that the concatenation, the double concatenation of this operator gives 0. In other words, this operator, which sends matrices to some other matrix, squares to 0, and it's a differential, it's clear. So you can take the cohomology. And this is the BST operator of which you take the cohomology, and you can put this on the computer and never worry about this again. But of course, for simple examples like this one over there, you can do it by hand. It takes about 2 minutes if you have enough experience.
So in your example in the corner, should I think of like v as x to the d and w as 0?
Exactly.
And then w being 0, that's the trivial?
Exactly. It's unfortunate. I should have said z to the I and z to the t minus I, because v depends on z, but you got it right.
Okay.
Okay, so this is something which is computationally not demanding. You can do it by hand, and you can program a computer to do it for big matrices. So now we have theories, defects, and fields, objects, one morphisms, and two morphisms, but we still need to know how to concatenate them, right? What is the fusion product and what is the operator product? Well, both is very simple. The fusion product is simply the tensor product of matrices, which is sometimes called the Kronecker product. And up to a sign, it's just the Kronecker product of y with the identity of size x and the identity of size y with x. And if you needed to, we could write down a big matrix that depends only on the entries of x and y for this matrix. So very simple way of constructing this. Then what is the unit morphism? We need the invisible defect. And what the invisible defect really wants to do is to equate bulk fields on the one side with bulk fields on the other side. So let's say my arm is now the identity defect. Here's one theory and here's the same theory, but I call the defects over here, the variables over here are called y, and the variables over here are called x. Just the same set of variables are just different names. Instead of saying left and right, I say x and y, right? So the matrix factorization, which corresponds to this thing, wants to set x equal y. So I write x minus y here, and then you can convince yourself by looking at it for half a second that this matrix here really squares to w of x minus w of y. So this is a matrix factorization of this w minus this w. So it is a defect, and one can show that this defect really does nothing on bulk fields. How it does something to bulk fields we'll discuss later, but this is the right thing to do. And geometrically it corresponds to the diagonal, so it wants to set x equal to 1.
That's not unique.
It's unique up to isomorphism. That there's different representations of the same thing, so the same up to isomorphism. One important consistency check is to compute what are the endomorphisms of these things. So in the bicategory, what would be all the fields that you can put on top, or that can sit on the invisible defect? But since the invisible defect is invisible, this should be the same thing as the bulk space. So the bulk space for a given theory W is this. And if you do the computation by computing this cohomology, this takes, I don't know, 2 to 5 minutes, I think, you find that it's actually true. So the endomorphism space of this matrix factorization is equal to that. I don't know whether there's any people here who care for such things, but for example, computing the endomorphism of this invisible defect or identity functor is the same thing as computing Hochschild cohomology. So the chiral ring is Hochschild cohomology of some category. Okay, so this is, okay, and then of course I have to tell you how do I concatenate local fields. So what is the vertical product? What is phi times psi in this case? Well, this is just matrix multiplication. Over here, these things were called capital psi. If I have capital psi and capital psi prime, then I just multiply these matrices which are representatives for the cohomology classes. Very simple. Questions? Good. So the first important theorem, which in this form was proved together with Daniel Murphy, says that this bicategory has adjoints. So earlier I tried to argue that if that orientation reversal, then there must be an X dagger for every X. So an X is a matrix factorization from W to V, from right to left. Then X dagger will be a matrix factorization from V to W. And what is this matrix factorization? So the thing that you will guess after thinking about it for a short while is that it's just a dual matrix, or the transpose matrix. Because there's some sign involved, there will be shifts and some signs, but it's basically just a transpose matrix. But what is interesting to know, what takes a lot of work, is to find the actual morphisms, the actual defect junction fields, evaluation and co-evaluation, which correspond to these cups and caps. And since I decided to keep the slides as tidy as possible, I don't give you the formulas, I just claim that we have formulas for this. So using a theory which we learned to appreciate very much, using homological perturbation theory and something called Atiyah classes, or associated Atiyah classes, we have very explicit formulas for both the evaluation and the co-evaluation maps. The co-evaluation maps are rather simple. They just involve derivatives of matrices, so partial derivatives. And the same is true of the evaluation, but there will also be residue expressions. But all these kinds of things are very hands-on. So computing residues is integrating, then you also have to know how to take derivatives. So if you have some background in calculus, then you can compute the bicategory of Landau-Ginzburg models. And that's what I want to do now. So first application. The first application is how a defect can act on a bulk field. So in this picture, we again, as always, have a defect X which goes from W to V. So outside there's the theory V, inside is the theory W. I don't make any assumptions what kind of V and W these are. And phi is a bulk field in theory W. So and now I want to view the defect as an operator, which can act on the field phi in theory W. It will produce something in theory V. And I do this by encircling the field insertion of phi with X. And since X is a topological defect, the precise size and locus of this bubble X, this loop doesn't matter, I can shrink it and collapse it on the insertion point of phi. And when I do this, everything will be not this pale blue, but this somewhat stronger blue here. And then I will have a bulk field. But what does this mean? I mean, how do I do this concretely? How I can actually compute? Well, I remember what I said 5 times already. All these diagrams, all these physical diagrams, are actually precise mathematical statements or expressions if I read them from bottom to top and from right to left. So let's do this. From bottom to top, I have a co-evaluation here, the inverse of rho, the right action. then phi, as I said, is the endomorphism of the invisible defect for W. Then here I have the right action of the invisible defect on X, and then the evaluation. I also claim that the evaluation is computed by taking some residue, and the formulas which were too big for me to show here collapse into something very nice and neat with no higher orders, and we get this precise statement here. So the new thing, which will be a bulk field in theory V, so that means it's a polynomial in Z, I get by taking all the partials of X, both respect to the little X variables and the Z variables, multiply them, take the supertrace, multiply with phi, which is a polynomial in X, because W depends on X. Then I divide by the product of the partials of W and take the residue. Now, all this stuff here depends on Z, and the X variables are integrated out. So this formalism really tells us what it means to integrate out. This directly gives you the result, and in the end you have a polynomial in Z. And this is the new bulk field. This is the defect action of the bulk field phi. I think that's nice. And there's this special, we can add to this by putting a field capital psi that lives on the defect X, and it just adds to a factor in the supertrace. Very simple. Okay, here's some special cases. If phi is equal to the identity, and psi is equal to the identity, so all this picture shows is just a loop, right? So it's the action of the defect on the identity field, and then I get something in the outside, in the outer theory, and this something is called the quantum dimension of X. The reason why it's called the quantum dimension is that, one reason, in the special case where we are not considering defects in some TFT, matrix factorizations, but just finite dimensional vector spaces, if I first compute the co-evaluation and then the evaluation, so now I have to evaluate EI star on EI, I get the number 1, which is delta II, as many times as there's the dimension of X. So first the co-evaluation and then the evaluation precisely gives me the dimension of the vector space. And since this is a quantum field theory, and for some other reasons, it's fancier to call it the quantum dimension. So that's a nice ring. This will play a role later.
So here, if I think about what this does to the R charge of the operators, I guess what's going to happen is that if there is no corresponding R charge on the other side, it just kills it.
That's true.
Otherwise,
Yes.
yeah.
So
Because it looks like it preserves R charge, right?
It does, yes.
Yeah.
So I don't discuss gradings and R charges at all, but all this works with R charge as well. Well, most of it I understand precisely, and the rest is true, but I don't understand very. But this we do understand. Another special case is where the outside theory is a trivial theory. So what you have in this diagram then is just a disk where you insert a phi in the bulk and the psi on the boundary, because now the outside theory is trivial, so this is a boundary condition. And then you get some residue expression for this bulk correlator, for this disk correlator. And that's precisely what Kapustin and Lee found in 2003, and a little later was also done very beautifully by Lazaroyo. And here we get it by drawing one picture. Yet another special case is when the inside theory is trivial, then of course phi is not there. And then what you get is you plug in a boundary condition psi, and you get out a bulk field in the outer theory V. And since there's nothing inside, all the residue will go away, and you get a map from the from the boundary field to a bulk field in theory V. So you have a map from boundary to bulk, and that's one of these locality maps that you have in closed topological field theory, and it's just given by the supertrace of this stuff. The special case where the boundary map psi is the identity is where you associate to a boundary condition a bulk field, and this association of a boundary condition to a bulk field is precisely what we call a boundary state in CFT, right? A boundary state is a coherent state in the bulk space, and in TFT it's this simple thing, And in Lambda-Ginsburg models, This is precisely given by the supertrace of all the partial derivatives of the matrix factorization. Another name for the boundary state here is the Chern character, because if we were not talking about Landau-Ginzburg models, but about B-twisted sigma models, it would be precisely the Chern character. And the Chern character features in the Hilsbuch-Riemann-Roch theorem, and so does this boundary condition. And maybe this I mention only quickly because I want to tell you about orbifolds. So the most interesting axiom of open closed topological field theory, the most quantum one, which involves a genus 1 diagram, is the Carqueville condition, a duality between open and closed strings. And it says that a certain trace in the open sector is equal to the overlap of boundary states, right? So we can prove this. We have a certain trace in the open sector is an overlap of the two Chern characters, which are the boundary, which are the boundary states, and the overlap is computing by computing the residue. And this is precisely the Landau-Ginzburg version of what is the Hilsbuch-Riemann-Roch theorem, a deep theorem in algebraic geometry for the B-twisted sigma model. And here's the one-line proof. That's it. So unfortunately, I only have 10 minutes left, so I just say open-closed duality means looking at cylinders. Cylinders are the same thing as annuli. And then there's two ways of computing this annulus, either by collapsing this, you get this, and you immediately have the Chern character from the previous slide, or you expand this until it hits the Y boundary condition. Then you have a boundary condition between trivial and trivial, and that's just this thing. Okay, but now to the interesting case. So far, I told you about defects, and that you can prove things like the Carqueville condition, or the boundary bulk map, or the this correlator. All of these things have been known for a long time. But now let's try and find something new. And this is the executive summary slide. So again, we start with a defect X between W and V. Actually, it could be any theory, A and B. And I want the defect to have invertible quantum dimension. So this loop thing, which is just a dimension for vector spaces, and which is the residue expression for Landau-Ginzburg models, this must be invertible. For Landau-Ginzburg models, this means that it's a non-vanishing complex number. And then I can take, then I can define a particular defect A, because if I have a defect X, which goes from W to V, then I can also go back with X dagger, and then I have a defect from W to W. So this is A. And the statement is that anything about, and A is a defect from W to W. Now, if there is such a defect A coming from an X which has invertible quantum dimension, which is the only condition, though it's a strong condition, then everything about the theory V, so the other theory, can be expressed and computed in terms of only the theory W and this defect A. And as we will see, one way to think of this A and why this is possible is to realize that A is a generalization of an orbifold group, or takes the place of an orbifold group or a symmetry group in a certain generalized way. Before we get there, I would like to give you the idea of why this is true. So the statement is that any correlator in theory V, in particular one that locally looks like this with two bulk insertions, but any other as well, can be computed, and this will be over here soon, in terms of something only living in theory W, but with the presence of the defect A somehow. Now, since it's topological theory, and since the invertible defect, the quantum dimension is invertible, so if I insert the quantum dimension here, it's the same thing up to a number. Let's say the value of the quantum dimension is the square root of 2. Then if I, or 2, then if I insert 4 such islands of theory W within theory V, then I get 2 to the 4. And if I keep track of the number of islands that I insert, that's just the same number. I can always keep track of this. But now I use that, it's a topological theory, so I can expand all these islands until they hit one another. For example, if I expand this one and this one, then here the defect will go down, the orientation will go down, and here it will go up. You can convince yourself that this will always be true. So after blowing up these islands for long enough, it will look like this, where always one orientation will be upwards and one will be downwards, or rather in the other direction. These things are isotopic to one another. But I can go on. I don't have to wait, so that there don't have to be these canals here. I can just squeeze them away. And these W theory canals, if they're squeezed away, they become the defect lines X, because, as I said before, X, dagger tensor X is the defect A. And so I have this network of defect A in theory W, where the network has only trivalent vertices, and I can compute this theory.
How do you get the orientations in the last picture?
That's a good question. There's one choice, and it doesn't depend on the choice. So if I say that this is A, then this must be A, and then it goes in like this. Okay. Well, these pictures may already be a bit convincing, but in order to prove theorems with that and find new equivalences between theories, I must develop some language how to actually do these manipulations. So I need to give a construction for bicategories. And that's what the next slide does. So now I start with a certain bicategory B of theories, defects, and fields, if you like. And I want that all these, this bicategory has adjoints, so the defects are orientable. Actually, the bicategory should be pivotal, but that's a detail that I don't want to stress. But we can later. Now I define a new bicategory, B-ec, for B equivariant, from this old bicategory in the following way. The objects of the new bicategory will now be pairs of old objects A and special one-morphisms from A to A, so defects of the theory little a, which I call separable Frobenius algebras. What does this mean? So first of all, this defect A should deserve the name algebra. So there should be a way of having two A's and producing one A. So there should be some sort of product. So that's a trivalent vertex, a particular junction field where two A's come in and one A goes out. So it's a map from A tensor A to A, a special junction field. And there should also be an invisible defect, sorry, a map from the invisible defect to A, and I denote it like this. So this long filled circle, there's the invisible defect coming in, and you get A out. And if it's an algebra, then you usually want it to be associative and unital, which is what these pictures tell us. So two ways of having three A's come in and one A coming out should be the same, associativity and unitality. Multiplying with the unit should give the identity. There's also the notion of a co-algebra, which means you put everything upside down. So a co-product is a map from A to A tensor A, and it's co-associative if you rotate this by 180 degrees and so on. That's what it means for A to be an algebra. Now, for A to be separable and Frobenius is that these things should be true. Maybe, given the time, I don't dwell on this very much. This part here is called the Frobenius property. This is called the separability with respect to the co-product, which is this thing here, from A to A tensor A. But what I would like to point out is that these pictures here are very similar to what you can call the moves, which allow you to go from any triangulation of a surface to any other one. So if we squeeze out bubbles, and if we have a certain associativity property, then we can start with any given triangulation of a surface, which will be the world sheet, and go to any other triangulation. And this is encoded algebraically by the defects that will, as on the previous slide, triangulate the surface, they should have this algebraic property. Because, of course, I could have started with 42 islands here, or any other number, and then I would get a finite network, a finite triangulation, but it shouldn't depend on this choice. So I want to have independence, and independence of the choice means invariance under Tachner moves, which is encoded in this way. Okay. Now if in my new bicategory, BEC, the objects are basically given by algebras, then a natural guess for the duomorphisms would be bimodules. So given an algebra, I can have two modules to the left and to the right, and this is precisely what we have here. So a bimodule between A comma A and B comma B would be an x that goes from A to B, such that there's a left action of B, 1x, and it has the usual properties of a left module, so you can either first multiply and then apply, or you can apply and apply, and that should be the same, and it should be uniform. Same for the right action. And these left and right actions of the defect A to the right and B to the left, they should commute. That's what it means to be a bimodule. And again, these are properties that you need in order to have invariance under the different choices of triangulations if there are defects present on the original worksheet. Similarly, two morphisms are given by bimodule maps, and the tensor product is defined by some universal property with which you can compute detail knockout. Okay? So these pictures encode invariance under triangulation. And now, on the next slide, I want to explain why this construction is called the equivariant completion. First, why is it called equivariant? So if I take my favorite bicategory, which is the bicategory of Lambda-Ginzburg models, and I take any object that is a potential W, and let's say this potential is invariant under the action of some finite symmetry group G. So I have a symmetry which I can gauge out with respect to into the orbifold. To any such symmetry defect, any such symmetry group G, I can construct a particular defect called AG, which is the direct sum, that is the superposition of all the invisible defects twisted by the action of G, say from the right. It doesn't matter whether it's left or right. You can, if we had more time, we could convince ourselves that twisting by the right simply means if we look at what this new defect I does to an insertion point in the bulk, it's just acting with the element little g on that thing. So IG encodes the action of the symmetry group on the bulk space. That's a natural thing to look at. It's a very natural defect to look at. And in terms of matrix factorizations, it's where G is the identity, so then we have the identity defect that we had before, and then we just apply G to Y everywhere because Y is on the right. Okay, so that's very simple matrix to write down. Now you check that this matrix factorization actually has naturally the structure of a separable Frobenius algebra. I won't show this, but this is very straightforward to do. And then we know that what we're supposed to do in the equivariant completion is look at modules and bimodules if we want to study boundary conditions and defect conditions in the associated new class of theory. So if we now look at matrix factorizations of W, that is at this bicategory, which I call HMF for homological matrix factorizations, and G equivariant ties that, then we can prove that this is equivalent to the boundary conditions in this equivariantized version of the bicategory, which by definition is modules over AG. So what I've said is that equivariant matrix factorizations, which by the work of, which in 2004, a paper by Diaconesco, Della Quilla, and Ashok, were seen to be the right way to describe boundary conditions in ordinary orbifolds of Lambda-Ginzburg models, G equivariant matrix factorizations. are the same thing, are equivalent as categories to modules over this special defect AG. So the whole formalism that I started to talk about on the previous slide, in particular, reproduces everything we know about ordinary orbifolds for lambda. I see that my time is up. That means that I should either stop now or be granted 3 to 5 more minutes to finish.
Let's say 5, with a firm 5.
Thank you very much. Okay. So we understand ordinary orbifolds. I should also explain why it's called the completion, but there's not enough time. But one can just show that the equivariantization of the equivariantization is the same thing as the equivariantization, so it's complete, this construction. More importantly, and this is really, what I will now say is the precise statement of the thing that I argued for pictorially 2 slides ago. Again, we take a defect X between A and B, and it has invertible quantum dimension for Lambda-Ginzburg models computing this residue, which is easily done. Let's say it's invertible. Then I can define A as X dagger times X as before, and I can easily show that this also has a separable Frobenius algebra structure. And most importantly, in the equivariant completion of B, in this bicategory, the object A, A, that is the capital A orbifold of the theory little a by construction, is the same thing as B, IB, but that's the same thing as B. So I can prove that this theory B is the same thing as the A orbifold in the sense that we discussed earlier. And this is true for any bicategory. This is true for Lambda-Ginzburg models, but there's other bicategories which are interesting from a string theory point of view, say, namely those bicategories which describe theories, defects, and fields in the A and B twisted sigma models. They involve Fukaya categories and derived categories, respectively. And they, of course, have something to do with homological neurosymmetry, and I believe that this formalism will be part of a generalization of homological neurosymmetry to the defect sector. Now, the final slide gives you an example, because I should tell you why this is actually a generalization of orbifolds, right? We saw that every ordinary orbifold by a group has this property, but now some very explicit equivalences between Lambda-Ginzburg models where there is no group. Recall that minimal A-type conformal field theories correspond to Lambda-Ginzburg models of this type here, A as an ADE, and there's also a D-type, D as an ADE, with potentials of this form. Now, this here is a matrix factorization of this W to AD plus 1, and this W to AD minus 1, because this times this plus this times this is this minus this. And now I can take my residue formula and compute the quantum dimension of this 4x4 matrix and find that it's 1 or 2, I forget. In particular, it's not 0. 1, I remember. And this means that matrix factorizations of the D-type potential are the same thing as this algebra here, X dagger tensor X. And we can also show that this is the identity on the A-type theory plus some other thing that squares to the identity. So in a sense, this is not a good example because I wanted to give you an orbifold equivalence between D and A that is not of an ordinary orbifold type, but now I rediscovered Z2, which I said at the beginning. But luckily, the slide has some more space, and this year we found that you can do the same thing also between A and E, therefore between A and D. So remember that the E-type minimal models and n equals 2 correspond to Lambda-Ginzburg models with this, and this superpotential. And then, just like we have explicit matrix factorizations of WD minus WA, we also have explicit matrix factorizations of WE minus 3 particular WAs, which have non-zero quantum dimension. And therefore, matrix factorizations of the E-type polynomial can be described by modules over this particular defect here, which we also understand very well in the A-type theory. So again, some very different theory, E-type Landau-Ginzburg models, can be constructed completely, both in the bulk, so in the bulk, boundary, and defect sectors, only by talking about these defects x staggered tensor x, the A-type side. Everything is very explicit. And you can't see this from the slide, but there's no group here at all. So these orbifolds, well here there's a group because J tensor J is I. This is not the case for x dagger x for the A and E type orbifolds. So this is really a new type of equivalence, and I think there's many others. Okay, just in time after my additional 5 minutes, thank you. I said that 2D TFTs with defects are to be described by bicategories plus some other structure. The other structure that I focused on in this talk is having adjoints, and I talked about the theorem proved together with Daniel Murphy that this is in particular the case for Landau-Ginzburg models, which leads to various nice applications of things that we already know, but in a new guise, which I think is more natural, is very natural. But we can also discuss something that had not been known outside, this I want to stress, outside the realm of rational conformal field theory, where many of the roots of all these constructions lie, because over the last 10-15 years, Fuchs, Runke, Schweigert, and collaborators have done a lot of work, and most of these results are inspired by their results. And as a brief outlook, one should do more of these orbifolds, and I'm sure that there's a lot of interesting relations to geometry between Landau-Ginzburg models beyond what is already known. Maybe this formalism can help to understand homological neurosymmetry better if you include the defect center. There's also relations between 2D and 4D theories for these Landau-Ginzburg models from the previous slide, and I would like to understand what these AE orbifolds, for example, or AD orbifolds mean on the 4D n equals 2 gauge theories to which they correspond. And one could also consider link invariance, but another time. Thank you very much.
Thank you. So, we have time for a few questions.
Vector space?
Well, I have a different question.
Okay.
So most of your pictorial intuition, it seems like it relied heavily on these theories being topological. So, but you said at the beginning that you imagine that so what can we extrapolate to the general 2D?
Yes. So the strongest result, I think, that comes to mind is that of Fuchs, Runke, Schweigert and Fröhlich, which says that given a rational conformal field theory with a few other more or less mild assumptions, like unique vacuum, non-degenerate two-point function, and so on, then every 2D CFT, rational of the same central charge, are generalized orbifolds of this kind, where it's really a statement about the full CFT, but the defects that you use in the construction are only topological defects. And topological means that, in particular, they are rational, so they preserve all the rational symmetry. Another thing is that one can consider any 2D QFT in a certain approach to QFTs via functors, and find that any QFT, if you only if you restrict to the topological sector, then you always have a bicategory, it always has the structure. How much of so certainly many of these things will go away, because defect fusion is maybe a sort of categorification of the operator product expansion. So in TFTs you have an ordinary product and there's no singularities. So there will be singularities, of course, if defects approach in general. And what the structure there is, I think, so I certainly don't know. And there's more to say, but maybe that's suffices.
Maybe a simple question. So these quantum dimensions of these defects in the Landau-Ginzburg set, Are they always integers?
No.
No, they're not.
No.
Are they always algebraic integers?
Good question. I don't know. In these ADE cases, yes, but that wasn't clear to me a priori. So they're cyclotomic numbers
For the AD.
for the ADE.
Yeah, but with some random potential, it'll depend on the parameters.
Yes. It's very nice.
All right, if there are no further questions, let's thank Nils again.